In this section, let's discuss how to get a complete picture for graphing polynomials and rational functions. Of course, you can use graphing calculator, but unless you get your window just right or the settings just right, and with rational functions, keeping in mind the asymptotes and so on. So now using calculus, we can get a really complete picture for the equation without even graphing or taking a look. It takes a little while to set everything up. I have about 5 steps that I usually use. But if you just set everything up, this will give you the points that you'll need, and also to be able to get a complete picture. We'll have an assignment on this later, just so that you guys get a heads up, and you will need to provide information on all of these. So I do not provide a lot of examples. When in doubt on your homework, you can use graphing calculator, for example, but it's just basically putting everything together right here. So like for graphing polynomials and rational functions are very similar, but let's focus on polynomials. We can always find y-intercept. You can plug in 0 for the x and you'll get the y, for example. X-intercepts, it really depends. Sometimes for some higher degrees like 3 or 4, when factoring is not possible, we really need technology there. So if factoring is possible, then you can find x-intercepts. If it's not, then you don't have to worry about it too much. Then we can find critical numbers by taking the first derivative and figuring out where it's 0 or undefined. Then we can also use number line to find intervals where f of x is an increasing, decreasing, and any max or min. You can also, step 3, use second derivative to find concavity intervals and points of inflection, if any. And lastly, we can recall end behavior from chapter 2, or limits at infinity, which is exactly the same thing actually from chapter 3. And then we can finally sketch a graph, and we can adjust the window and the scale if needed. So here's an example, and I'm trying to be true to the homework. Here it has some big numbers, large numbers, so I wanted to provide a similar example. So here we have f of x negative 2x cubed minus 9x squared plus 108x minus 10. Y-intercept is usually the constant, so x is 0, so we have 0, negative 10. X-intercept, well, we can take a look, you can try, but it does not look factorable, so we just not going to list them. Okay, let's proceed to step 2 with the first derivative. I took that, I got negative 6x squared minus 18x plus 108. Polynomials are always defined, so we can just set it equal to 0. Notice how you can pull out negative 6, in fact, and I kept it outside, and we get x squared plus 3x minus 18 equal to 0. I think that's factorable. So we're getting x positive 6 and negative 3 would work. So the critical numbers are actually x equals negative 6 or x equals 3. We can plot them on the number line. Notice how I picked some test points on the number line, usually to get the complete picture. I put f prime of x and f of x. So again, we'll put negative 7. Remember, I like to use the factored version right here to plug it into. So negative 7 plus 6, that will give us negative 1. Negative 7 minus 3, that will give us negative 11, I believe. So negative times negative is a positive. But we have negative 6 on the front. So the product of 3 negative numbers will give us negative, which means the original function is decreasing or going down, as I indicate with an arrow. Then between negative 6 and 3, I picked 0. 0 is always the easier one to test. Notice how we'll get 0 plus 6 is 6, 0 minus 3 is negative 3. So we'll get negative, but times negative 6 will give us a positive. So the function is increasing there. And to the right of 3, I picked 4, and 4 will give us positive, but times negative 6 will give us negative again, so the function is going down. So note how it's decreasing from negative infinity to negative 6, and then also from 3 to infinity with our critical numbers. It's increasing between negative 6 and 3, and notice how we can even visualize it. It looks like a minimum at negative 6, but a maximum at 3, and we can find the y value. So let's take a look by plugging it into the original. I got negative 6. Be careful with signs a little bit. I got 550 for the y by plugging it into the original, f of x. And then I got 3, I think it should be negative 550, the usual typo, so let me fix this. Yeah, otherwise how can it be a minimum? I got negative 550 there. Maximum 3 and then 179. Okay, let's proceed to step 3. Second derivative happens to be negative 12x minus 18. We can move that to the other side. So I'm getting x equals to negative 3 halves. We can test that with a second derivative. I picked something easy, like negative 2 and 0 to the right of it. I'm plugging into the second derivative. So negative 2 times negative 12, that's 24 minus 18 will give us positive. And then 0 will give us negative, 18 will give us negative. Notice how sign is switching. So we have concavity interval, but we also have an inflection point. So concavity, it's concave up from negative infinity up to negative 3 halves. It's concave down from negative 3 halves to infinity. Inflection point, I just use decimals to make it easier. So it's negative 3 halves and negative 185.5. Okay. Step 4, end behavior. If you recall, let's take a look at the original function, if I can scroll up real quick. Okay. To get the end behavior, we must focus on the leading term, which is negative 2x cubed. Notice degree is 3, but the leading coefficient is negative. So going back to here, I always remember, if it's odd, I always remember y equals x cubed, and it looks like this. And notice the end behavior, you can just focus on the two ends. They look like this. So the first end is going down, the second end is going up. Negative leading coefficient reverses this. So the first end is going up and the second one is down. If you're having difficulty remembering this, let's analyze this a little bit. If you remember, the leading term was, I'm going to write this out, f of x equals to negative 2x cubed. When x is going to negative infinity, we'll have a large negative number. Remember, negative number cubed will give us negative, but times the negative 2 will give us positive. That's how come it's going to positive infinity. So the first end is going up. When x is going to infinity, on the other hand, the f of x is going to go to negative infinity. So the second end is going down. So you can always analyze it more if you need to. Now graphing, excuse me. I decided to count y's by hundreds, and if you're going to look in your calculator, I advise you to fix that and maybe put the scale by 100 so it doesn't look too big or too thick. So if you recall, we had a minimum. Basically, I just plot the points first. I put the minimum at negative 6 and negative 550 about. I put the inflection point, which was negative 1.5, negative 3 halves, and negative, I think it was 185.5, something like that, so closer to negative 200. I put the y-intercept at negative 10, very close to 0, and then the maximum at 3, I think 179. So I plotted all of them and then I started joining them. Remember the end behavior, the end was going up. So basically I joined it all the way up to negative 6. The function is decreasing, if you remember, up to negative 6. Then it's increasing between negative 6 and 3. So, excuse me, I'm starting to draw. Let me erase that. But right at that point, excuse me, I must undo. Okay, let me undo that. I erased too much. But it's increasing from negative 6 to 3, and which is what I did. And then from 3 on, it's decreasing and the end is going down. The inflection point, you don't really do that much, but sometimes I do use concavity. It was concave up all the way up to negative 1.5. And notice, you don't always notice the inflection points. Sometimes you really notice them, like sometimes they really switch, like this could be an inflection point, but sometimes it's not very noticeable, like right here. For example, inflection point would be right about here, so it's not very noticeable. So it's not very noticeable for this one, I don't think, but it does switch. And so this is how we got the graph. So basically I put the ends together with a max, min, and inflection point, and this is what I got. Okay, now let's take a look at another example. How about x to the fourth minus 4x cubed? This is one of the easier one, but I wanted to demonstrate the even degree one. Y-intercept, notice there is no constant, so it's 0. So it's actually origin, 0, 0. X-intercept, we can actually factor here. So in fact, I pulled out x cubed, I believe that was the largest. And we end up with x minus 4 equals 0. So x equals 0, which is usually 0, 0 is both x and y-intercept, or 4, 0. Okay, moving on to first derivative, happens to be 4x cubed minus 12x squared, set it equal to 0. You can pull out 4x squared, so I got 4x squared times x minus 3 equals to 0. Notice 4x squared equals to 0. You can divide by 4, you can take the square root, you'll still get 0, and then x equals 3. Okay, so we plot them on the number line. I purposefully make them bigger, and I make my test points either in different color or smaller. So I picked -1, 1, and 4, just something easy. Again, I usually list the first derivative and then the original function. So -1, plug it into the derivative, factored form. -1, the square is going to be positive, but -1 minus 3 is going to give us negative, so the product is negative. So the function is decreasing. But if we plug in 1, notice same story. We get positive, and then 1 minus 3 is negative. It's still negative. So the function is still decreasing. But then at 4, we're going to get both pieces positive, so the product is positive. So the function is increasing. So it looks like we have a min at 3, but we don't have max or min at 0. It could possibly be an inflection point. In fact, it happens to be an inflection point, but we don't know. So it's decreasing. I did not separate it with a 0 like this. It's decreasing from -infinity to 3. Basically, unless you have an asymptote, you don't need to separate it. And then it's increasing from 3 to infinity. Okay, and we do have a min at 3. I plugged in into the original function. I got -27. So we have a min. So 0, 0 is not an inflection. Could possibly be not a max or min, could possibly be an inflection. Notice it happens to be an inflection. The second derivative is 12x squared minus 24x equals to 0. We can pull out 12x, and we get x equals 0 or x equals 2. Now we can plug into the second derivative. I plugged it in, and we got, I picked some points. I don't think I mentioned which ones. You can pick -1, for example, and you'll get negative times negative gives you a positive. You can pick 1. Positive times negative gives you negative. You can pick 3, and then positive times positive gives you positive. So notice the thing is, the sign does switch, so we have a couple of inflection points there. And we have concavity points. So it's concave up from -infinity to 0, and then also from 2 to infinity. It's concave down from 0 to 2. And inflection points, by plugging them in the original function, I get 0, 0, and 2, -16. And now we can finally graph. Oh no, we need something else. We need end behavior. Remember, y equals x to the 4th. It's even degrees, so both ends are going up, or you can do the limits. They're both going to infinity, because x to the 4th, whether it's negative or positive, they're going to go to infinity. Okay, so how do I graph? Here is the scale that I used. I plot 0, 0, and for 2, -16, and 3, -27, I didn't use the right scale, but I just basically labeled them on the y-axis. And then I used 4, 0, if you remember, that was x-intercept. Then I remembered, so I put the end behavior. I remembered it was concave up to 0, and it was. And then at 0, remember, it's inflection point that switches concavity, so it looks a little bit more noticeable here. Right here. So it switches concavity, becomes sort of upside down, concave down, all the way up to 2. And then at 2, it switches again to concave up. So notice it's going all the way up to the minimum, and then it's going up again. So here I used concavity a little bit more to piece it together than in the previous example. And increasing, decreasing should still make sense here. It's decreasing all the way up to 3, and then it's increasing from 3 to infinity. So I used concavity quite a little bit here. Okay, so this is it for polynomials. I'll do the rational functions in the second part.